In today's lecture, we are going to discuss types of mechanism, what are the different types of aliphatic nucleophilic substitution reaction, and then we discuss SN2 mechanism in detail. And we in detail discuss its evidences such as kinetic and stereochemical evidences, and in detail we discuss Walden inversion. So let's start. Many types of aliphatic nucleophilic substitution reaction are possible depending upon what type of substrate you use and nucleophile, leaving group, reaction condition. But all that type of mechanism, the one thing is similar. The attacking reagent carries its electron pair, and by using its electron pair it attack on electron deficient center or substrate. So in all those type of reaction, similarities are greater than differences. The most common types of mechanism are SN1 and SN2. Now we will discuss in detail SN2 mechanism. Contents are, we briefly see its introduction, what is the nature of CX bond, then we will discuss its evidences such as kinetic evidence and stereochemical evidence, and then we will discuss Walden inversion. So let's start. The designation of SN2 stand for substitution nucleophilic biomolecular, means during this reaction nucleophile leaving group, this leaving group X is substituted by Y nucleophile, and this reaction is a biomolecular reaction, means during the reaction two molecules are involved. One is our nucleophile and next is second one is substrate. The IUPAC designation is A and DN. AN mean attachment of nucleophile and DN mean detachment of nucleophile. In other words, we can say that detachment of leaving group, because you can see from this equation that this leaving group is leaving with its electron pair. We can also call it as nucleophile. So A and DN means in a single step a nucleophile is added and a leaving group departs. The another thing important to note is that during the reaction backside attack occur, mean nucleophile attack 180 degree away from the leaving group. You can clearly see that this Y is attacking on carbon 180 degree from X, means there is 180 degree angle difference between attack of the nucleophile and departure of the leaving group. The reaction complete in single step and no intermediates is formed. The CY bond is formed and there is a simultaneous bond formation and bond breakage. Mean at the same time CY bond is formed and CX bond is broken. And this transition state 1 shows that partial bond formation between Y and C carbon and partial bond breakage between carbon and X, a leaving group. Another thing important to note is that during the reaction when backside attack occur, we get inversion of configuration. Inversion of configuration means the group which are present on this position, you can clearly see from the equation that these are now on the opposite side. So we get inversion of configuration when a backside attack occur. The group which are on the left side are now present on the right side of our nucleophile. The another thing that comes in our mind, that we know that bond breakage required energy. So where does the energy come from to break CX bond? This energy is supplied by the simultaneously CY bond formation. We know that bond formation release energy and bond breakage required energy. For to break bond, we have to provide energy, and during the bond formation energy is released. So when CY bond is formed, the energy is released. This energy which is released is utilized to break CX bond, carbon nucleophile carbon leaving group bond. Okay, is broken by using energy which is released during carbon nucleophile bond formation. So CY bond formation release energy which is utilized to break CX bond. Next, we discuss that simultaneous bond formation occurs. CY bond is formed at the same time CX bond is broken. So how this is possible that at the same time bond is formed and bond is broken? There is no possibility that Y and X get attached to the carbon at the same time, and carbon have more than 8 electron its outermost shell. It contradicts octet rule, which is not possible. So this is was explained by hybridization approach. Hybridization says that the carbon first changes its hybridization from sp3 to sp2. Here this is carbon which is sp3 hybridized, and to one of its hybrid orbitals, the orbital of our leaving group is overlapped. So when it changes from its hybridization from sp3 to sp2, it have now three hybrid orbitals and one unhybrid orbital p, which is perpendicular to the hybrid orbitals, and which orbital is unhybridized, to which the leaving group is attached. You can clearly see that to that this to this p orbital, the orbital of our leaving group is attached, overlapped. So when it get converted into sp2 hybridization, the nucleophile orbital attack or overlap with p orbital, and these orbitals get detached. So in this diagram you can see that the orbital of nucleophile is attached with the p orbital of our reaction center, and nucleophile is the orbital of nucleophile is free. For better understanding, I have just shown one orbital. Then when this nucleophile orbital is attached with p orbital of our substrate, this again changes its hybridization from sp2 to sp3. Now you can clearly see that this hybridization from sp2 is changed to sp3. The p orbital is now get hybridized into sp3 hybrid orbitals, and you can clearly see that these orbitals which are on the left side are now present on the right side, and we also get inversion of configuration. So what happened, what thing is explained by the hybridization explained that first the hybridization changes from sp3 to sp2, and one of the orbital is get converted into p orbital, to which the leaving group is attached, which is perpendicular to the hybrid orbitals. To the other lobe of the p orbital, the orbital of nucleophile attached, and leaving the orbital of the leaving group leaves or get detached. And in the next step, the sp2 hybrid carbon is now again converted into sp3 hybrid carbon. Next, now we in detail discuss some evidences of SN2 mechanism. The first evidence is kinetic evidence. Since we have discussed earlier that during the reaction two molecules are involved, one is nucleophile and other is substrate. So the order depends upon two things: the order, the concentration of our substrate, and the concentration of our nucleophile. So with respect to our substrate, the order is first order. With respect to nucleophile, the order is also first order. But overall, the order depend upon two things, two reactants. I mean the concentration of two reactants. So it is second order reaction. Another thing important to understand is that the 2 in SN2 stand for bimolecular, not second order. Means the 2 in SN2 stand for the reaction is bimolecular. During the reaction, two molecules are involved. Molecularity is somewhat different from the order of the reaction. Molecularity tell us means how many molecules are involved during the reaction, while order of reaction tell us that how many times the rate of reaction depend on the concentration of specific reactant or all the reactant. We consider this by taking a example. Let's we have 4 molecule of Y, and we have only one molecule of Rx. So what happened during the reaction? Only one molecule of Ry is formed. Why? Because only one molecule of Rx is available which react on which Y attack and get converted into Ry. So what is controlling the reaction? Which reactant is controlling the reaction? Just Rx, because it is present in small amount, and you have clear concept about limiting reactant. The reactant which is present in small amount control the reaction. So in such situation, the order depend only on the concentration of Rx. Let us take an example. If we have a large excess of nucleophile, means solvolysis, if a reaction occur in such a condition that in which solvent is acting as a nucleophile. Let's suppose reaction is occurring in alcohol where OH group is acting as a nucleophile. As OH group is present in large amount, the order because of that OH group or nucleophile is 0. Then order only depend on the concentration of reactant. Such order of, and still the molecularity of the reaction is 2, because still during the reaction 2 molecules are involved. One is our substrate Rx and other is our nucleophile which is OH. Molecularity just tell us how many molecules are involved, and while order tell us how many molecules, not how many reactants are controlling the reaction. So such a reaction in which are initially SN2, but by taking one reactant in large excess we convert them into first order reaction are known as pseudo first order reaction. Next, this was all about kinetic evidence, but kinetic evidence is not enough to discuss whether SN2 reaction is occurring or not, because there are many reactions in aromatic system which occur by SN2 mechanism, which follows second order kinetics. So just looking at the kinetics, we can't say that this reaction is performing through SN2 mechanism. We need some more evidence. Then second evidence is stereochemical evidence. Stereochemical evidence means during the reaction, if we get inversion of configuration, it confirms that SN2 reaction is occurring. During SN2 reaction, what happens? Nucleophile attack from the backside and leaving group departs. We get a linear transition state where we have partial bond formation of Y with carbon and partial bond breakage between carbon and X leaving group. And when we get product, we get inversion of configuration. The group which are present on the left side are now present on the right side. So during the reaction, if we get inversion of configuration, it confirms that the mechanism that is occurring is SN2 mechanism. This the concept of this inversion was given by Walden and is known as Walden inversion, and this mechanism or this concept was given long before SN2 mechanism was formulated by Hughes and Ingold. But what Walden actually did, Walden give number of examples to uh, give the concept of Walden inversion. Walden first gave uh, let's